So we are officially being recorded at this point. What we'll do today is to continue our discussion on Tuesday. Do you guys still remember what was the last thing that I talked about on Tuesday? NAND gates, okay? And what was the significance of the previous lecture? What was the starting point and where did we end with Tuesday's lecture? Yeah, go ahead.
Other logic operators for NAND gates?
Exactly. So we started off with physical quantities, electrical charge, transistors, and stuff like that. And then we ended up with logical quantities, true, false, because NAND 2, even though it's not a regular Boolean expression or regular Boolean operator that we use on a daily basis, it is still a Boolean operator. Okay, so that was the significance of the previous lecture. So what we'll do today is we'll continue with that, and we'll talk about, first we'll talk about how NAND 2 by itself can emulate all of the other operators that we already know. Okay, so we'll start with that. And to do that, I can either read from my own notes, because it's all there, which is going to be very boring, so I'm not going to do that. Instead, what I'll do is I'm going to use my tablet, and we'll work out those equations, in class. I do not expect you guys to be able to derive the equations. So if you feel that, okay, I don't understand enough Boolean algebra to do all this, that's okay. But once I explain it, I'm hoping that all of you can understand the derivation. Is that okay? So there's a difference between the ability to derive the expressions versus the ability to understand the expression, understand the derivation of the expressions. Okay? So here we go. Turn on my tablet. All right. Takes a little bit of time. USB connected. All right. So this is my tablet. Whatever I draw here, will on my tablet will appear up here. So let's go ahead and take a look at an NAND 2 gate. So when we say NAND, okay, I'm going to use C++ notation here, because you are all familiar with C++ notations already. So in C++, okay, this is I'm going to use a medium thickness pen here. What is an exclamation point in C++? It's not logical not. Okay, there are two nots in C++. One is bitwise not, the other one is logical not. So for the most part, at the beginning of this class, we are only talking about logical operators, but not bitwise operators. Later on, then we'll start to get into bitwise operators. Okay, but this is familiar, right? This is basically the usual not. So we'll let x represent one Boolean variable, which means it can be true or false. Do you recognize this part? Double ampersand is logical not, logical and, also known as conjunction. Okay, and then we use y to represent the second variable. This is NAND. Okay, it is negating a conjunction, and therefore it is a NAND. Is that okay? So I'm claiming that this is doing the same thing as this. Okay, so I'll just kind of do a quick draw of the circuit that you saw the other day. And I'm going to simplify certain parts of it because it is not important from the discussion perspective of just being a circuit here. And remember, as long as the technology is working, everything that you see on the projector is also getting recorded. So there's no need to kind of frantically copy everything onto your own notebook. So you might want to just kind of focus on the concept and ask questions when you have questions about the concepts. Okay. And I'm just going to be correct here and use two bubbles. There we go. So we have two P transistors on top, two N transistors at the bottom. And this is the circuit that you are familiar with, especially the early lab section, because you just did this, right? Okay. And the output, okay, so we'll say the output here, I'll just call this Z here. So the output of this circuit is here, and this is my output pin. I'll call this Z. So now we have a, on the left-hand side we have the C expression, on the right-hand side we have a circuit diagram that claims to do exactly the same thing. Now the notes, already kind of goes through all the scenario of, why these two are quote-unquote equivalent. So we'll just kind of quickly go through, that stuff and go like, okay, why are these two equivalent? So I've got to think of a way to do this in a convenient way. Let's see, this is copy, this is layer, and can I copy? Nope, not easily. I'm just looking for a quick way to copy and paste. So I suppose I can use a razor and then copy. There we go. So we're gonna drag this one to the next page. There we go. And we'll put it here. There we go. All right, so I'm keeping the other one around as a template. So this one is just, a copy of that. So the first question is, what if X and Y are both low? In other words, they're both 0. So at this point, I'm making the assumption of the lack of a voltage, or 0 volt, is representing false or 0. The presence of a voltage is representing 1 or true. Is that okay? All right. So what if X is 0 and Y is 0? So we think about, what if, okay, switch back to a pen. What if X is 0 and Y is 0? In other words, I'm confirming that X is 0 and Y is 0 with this notation. If X is 0 or low, what happens to this transistor? Is it going to be on, which means it's connecting, or is it going to be off, which means it is open, it is not connecting? It's going to be on, because this is a P transistor. With a P transistor, when the gate has an absence of voltage, the device turns on, which means it connects. Is that okay? Same thing happens to this transistor over here. So now, Z, which is the output, has 2 paths to go to a high voltage, which also means Z will get a value of 1. Is that okay? Because in this scenario, this is connecting, and this is also connecting. What about the N transistors? What about these two guys? Because they're N transistors, the absence of a voltage at the gate turns off the device, so they are not connecting. So there's no way for this output pin to have a path to go down to the ground, which is 0 volt. As a result, the output pin Z is only connecting through the top 2 transistors to power, which means it is experiencing a high voltage, and therefore it has a voltage of, it has a representation of 1 or true. Okay, so we'll just write down here, Z equals to 1.
Professor,
yep.
Could you repeat that? Could you repeat what you just said?
Okay, sure. So I'm going to use a different color here. So I'm going to use a red color, okay, to represent whether a transistor is connecting or not. Okay. So we'll take a look at this transistor first. Okay. We'll focus on this transistor and ask the question: is it going to be connecting or not? This is a P transistor because of the bubble. But the bubble is also basically saying if the input is high or if the input is 1, then it is off. If the input is low or 0, then it's on. But right here, I'm saying both inputs are low. So X connects straight to this one, and it is low, and therefore the device is on. If the device is on, it is connecting. So I'm going to draw a solid bar here to represent this transistor is on. Same argument applies to this transistor over here, okay? Because both inputs are on, and you can see how Y is connected to the gate of the second P transistor. So the second P transistor is also conducting, and therefore we have conductivity here. So are you Are you okay? Because I'm explaining to you. So I got to make sure that you are okay with this explanation. Is that okay?
Yeah.
All right. What about the AND transistors? The AND transistors need the gate to be a high voltage or 1 in order to turn on, but both of these input pins are zeros. So that means both of the AND transistors are off. When they're off, they're not connecting. So I'm just going to use a cross here to emphasize that these two transistors are both not connecting, they're both open. So now it is pretty clear if you are here at the point Z and you're going like, okay, where can I go? You can only go to the power or positive voltage. There's no path to go to 0 volt or the ground plane or the ground rail. Questions back there? Yep. Yeah, go ahead.
So the terminology open means it's not connected.
That is correct. Yeah, when we use the term open in circuits, it means it is not connected. So it's open versus closed. Open is not connecting, the switch is off. Closed means the switch is on and it is connected.
Okay.
Yep.
So the two NAND transistors are off because they have low voltage and you need a high voltage for them to be on?
Yes.
Okay.
Yep, go ahead.
To help explain a little bit, one way that I learned about on and off is that you can think of it as a literal gate or like a bridge. So when a bridge is open, it's on and no cars can pass through. When the bridge is closed or off, then you can have things that are going through. That's how I explained it. Okay.
Yeah, I know it's confusing because when we look at doors, right?
Yeah.
When you open the door, it connects, right? When you close the door, there's no flow.
Because I was thinking of like valves, like you know how you were talking about plumbing in last class. I was thinking, well, when a valve is open,
Yep.
that means things are passing through.
Yep.
So it's just the opposite.
Yep. So, but now we got it clarified. Is that okay?
Yeah.
Okay.
Thank you.
Sure. Absolutely. It times out is interesting because it times out the PC. Even though the tablet is active, the PC thought, hey, nothing has happened for a long time because I have been interacting only with the tablet, and that's why it timed out. I just thought it was kind of funny that I have only been using this. I have been using it. How come it's timing out? Well, that's why. Okay, so we're gonna. It did preserve the original picture. I wonder if I can still paste. No, it wants to cut it again. So, okay, that's fine. Okay, so we'll go ahead and copy this and use a new page and paste it here. Okay, so this time we'll look into the situation where X is on and Y is on. Okay, and see what happens. So this time we say X is 1, Y is 1, okay? And we'll try to figure out what is going to happen in this case. Now this one is actually easy to figure out because everything is opposite to what it was in the previous slide, okay? You can see how, okay, this is kind of cool because I get to use this pen to draw, but I have to use the mouse to actually point on the other side. So if I can draw with my left hand, that would be like perfect because I can now do both at the same time, like a DJ. Yeah, like a DJ. Okay, so X is 1 here. Okay, so this is X. So this gate, which is a P transistor, is experiencing a high voltage. So is it on or off? It's off, which means it is open, it's not connecting. Okay, so we'll go ahead and denote that this is now not connecting. Same thing applies to this one, okay? But what about the AND transistors? Both AND transistors are on. The key is both are on. In other words, this transistor is on, it's connecting. This transistor is on as well, it is also connecting. It is essential that both AND transistors are on because if only one of them is on, there's no path from Z to ground. Because these two transistors, the two AND transistors are connected in series, which means they have to be both closed in order for the entire circuit to be connected. Is that making any sense?
Yeah.
Okay, so in this case, Z can find a path. Okay, Z can find a path to ground, but it cannot find a path to the higher voltage. So that's why Z has a value of 0 instead of 1.
If it didn't go to ground, but it was blocked from power, would that cause like error readings or?
Say that one more time.
If it was blocked from ground and power?
Then it's called floating. Okay, now this particular circuit does not have that behavior. In other words, no matter how you specify the 0 and 1 for X and Y, the output has to connect to one of those two rails, either the power rail or the ground rail. But there's no way that it can connect to none of the above. Now there are other circuits that can do that. Now when that happens, Z is called high impedance. It is just quote unquote floating. There's nobody actually specifying the electrical potential on that wire. Yep.
Is it possible, maybe on a different circuit at least, that it has a path to both ground and power? And what would happen?
Well, I can draw a very simple circuit that can do that. And bad things will happen. Okay, so I'm going to draw this circuit here, okay, and you definitely do not want to do this. Okay, if you do something like this in an electronic technology class, the professor will kick you out of the lab. If the professor doesn't, the fireman will. All right, so I'm going to draw that circuit here, and of course the cricket likes that too. Okay, so here's it doesn't really matter what type of transistor we have here, okay? So there's one transistor. This is an N transistor, okay? So if this is an N transistor, when this is 0, then nothing happens, right? Because when the gate is a 0, an N transistor is off, which means it is an open circuit, nothing happens, okay? So what if this is a 1? If this is a 1, then we are closing the circuit. The transistor is on, we are closing the circuit. So now we have what we call a crowbar from power to ground. It is equivalent to, now do not ever try this, okay? It is equivalent to sticking in a thick copper wire to the 2 terminals of the outlet, okay? Now, I'm not trying to ask anyone to experiment and find out what's going to happen. What do you think is going to happen?
Bad thing.
It depends on the wiring of your house. If it is properly wired and the breaker, everything else is done to code, then nothing too bad is going to happen. Okay, there will be a burning smell, before the breaker pops, and then your parents will ask, what just happened? Your smoke alarm would likely to go off because of the smoke. Okay, because there's some plastic stuff is going to burn for sure. Okay, but your breaker is going to break because the amount of current passing through that wire is going to exceed 30 amps, okay, which is what most of your circuit breakers are set to, okay? So your circuit breaker will do its job, it will just pop and break. On the other hand, if the wiring of your house is not done properly, before the circuit breaker has a chance to break, it's going to cause a fire at some kind of junction. And that's usually up in your attic, where it's really hot, dry, and if it's not inside the junction box, the flame is going to be exposed to flammable material, and then the house is going to catch fire. As I said, bad things will happen. Okay, what if this is inside a computer? That transistor will vaporize. Right? You would think that that's not possible, but it will vaporize. It will get so hot that it will vaporize. Okay, so the silicon and the substrate material will actually vaporize. But guess what? All that stuff is inside what we call packaging, which is kind of like epoxy plastic thing, right? So it has nowhere to escape. So the pressure will keep building up until it explodes.
I'm glad I did this question.
So somebody asked this question, I'm just answering that question. But we do have one more scenario that's kind of interesting that I have to explain. So let me scroll back to the page where I'm copying everything from, and then we'll have one more analysis, and then we are done with the analysis of this circuit here. Okay, you have copy and then paste. There we go. Okay, so this is the time. Oops, switch back to the pen and use the right color here. So this time we have one input being a 0, the other input being a 1. Okay, so we haven't really looked into this particular scenario. Okay, so in this case, the way I drew this diagram is when X is low, then this transistor is on, right? Because it's a p-channel transistor, and when the input is low, the transistor is on, it's connecting. So we'll go ahead and draw a solid bar here to say that this guy is on. But the matching AND transistor is going to be off. Okay, so if you track down X, here, it is also going to the lower AND transistor. So this one's going to be off because it's an AND transistor and the input is low. So we'll put a big cross here to basically say this is open, it is not connecting. And then we track down Y. Okay, so Y is 1. It is going to this transistor here. And because it's a P transistor, the input is high, so the device is off, it is not connecting. So we put a big cross here, and then the corresponding AND transistor is going to connect here. Okay, so when you look at this circuit, what is Z connected to?
Power.
It's connected to power, because the path to ground is interrupted by the transistor that is off. But you only need just one path to go to power in order for it to be connected. So that's why in this case, Z is also a 1. Is that okay? So now when we look at the truth table of how X, Y affects Z, it would be the truth table of a negated AND, and that's why it is called a NAND gate. Is that part okay? Yep.
In that example you gave where the power and the ground were connected through a transistor, what if there's an output?
What if there's an output like a LED, some kind of motor, load?
Whatever, just a connection to the power and the ground, but there's an output.
Okay, so the question is, what if Z here, okay, what if Z here is connected to something, right?
Yeah.
Okay, so let's say it's connected to a light bulb. Okay, so I'm going to draw a light bulb here. So now the question is, where's the other end of the light bulb connected to? Because there's only one output out of this circuit, but a light bulb has 2 terminals. So now you have to tell me how you're connecting the other end of the light bulb, because if you connect the other end of the light bulb to ground, then the light bulb turns on when Z is a 1. If you connect the other end of the light bulb to power, then the light bulb will light up when the output, when Z is at 0.
I actually meant like how there's a connection to power.
Uh-huh.
Then there's also a connection to ground. But in the example you gave where you said it would explode, there was no output, right? So what if it has a connection to power and ground, but there's a Z? Does that make sense?
Do you want to draw that picture?
Yeah, that's exactly what I was asking. That's what you're talking about, right? Where
Yeah.
It's the other circuit, I think.
Okay, so let's see if I can draw that circuit.
I think the crowbar circuit. Yeah, the crowbar.
The crowbar, like this.
Page 4.
Except there's this output, there's a Z.
There's a Z.
Yeah,
load or something?
I guess.
Okay, so this is equivalent to holding onto that copper wire as you stick it to both terminals of the outlet.
Alright.
Z is gonna say it's hot.
So is Z gonna vaporize too?
Huh?
Is Z gonna vaporize?
Z is gonna be vaporized?
Yeah, it's like
No, well, it's temperature-wise, yes, okay, because the heat will conduct to Z, but it has no specific. It's hard to say, whether it's going to experience a high voltage or low voltage in this case, because it depends on the resistance of the rest of the circuit.
okay.
Because everything has resistance. It's only a matter of how much resistance. Yep. All right, but don't do this. You can, the only time you can sort of do this and not really cause a whole lot of problem is when you use alkaline batteries. So when you have like a AAA battery, you hook up the terminals, like the plus to the minus, okay? The wire will get really hot, okay? But it typically won't explode. And that's only because the internal resistance of an alkaline battery is large enough to limit the current so that it's not going to do something that's really, really bad. Okay? I don't know how many of you have done this. You know, you put batteries in your pocket, and then somehow your keys just so happen to connect the terminals. It happened to me once. It got really hot. But that's only because it was alkaline batteries. If it were nickel metal hydride or nickel cadmium batteries, you know, my pocket would have caught on fire. Because those batteries have a very low internal resistance, so the wire can get so hot it can glow. If it can glow, it can light up something, like, you know, my pants. Huh? Wow. Now, lithium-ion batteries are even worse, because instead of lighting up my shorts, it's going to explode in my pocket. So there are all of these, you know, kind of not so desirable you know, consequences depending on the battery chemistry. Okay, so any other questions? Any additional hypothetical experiments?
Not yet.
Not for the time being. Yes. Okay. Cool. So we are, you know, we are done with the discussion of some pretty important material now. So let me sign into Canvas first, so I can show you, you know, how much material we have covered at this point. Yeah, when we're kids, we do all kinds of experiments, like licking a 9-volt battery. Yeah. No, 9-volt batteries, you know, if you lick it, it's not going to explode or anything, but it will give you a very tingling sensation on your tongue.
I actually have a question.
Yep.
So for the transistors, are the P always grouped together and the N always grouped together, or were they?
The P's are always connected to the power rail, and then the N's are always closer or connected straight to the ground rail. Yep. And that's because the source of a P transistor has to be of a higher voltage than the other terminal, and then the other way around for N transistors. Mm-hmm. Is anyone going to electrical engineering in this class? Cool. Okay, so you guys will know a lot more than I do in a few years, because you will have to study device physics, which is actually studying what is going on inside the transistor, you know, to explain, you know, how does it turn on, how does it turn off, you know, how does it work in general, and stuff like that. So we are almost completely done with this one, except for the derivation of, you know, how the other Boolean operators. So I'm gonna explain, you know, that stuff using the tablet. There we go. Okay. So the first one is, I really just want this, but I have NAND. What do I do? Okay, so if I only, okay, if I restrict you, okay, and I define the NAND operator in C++, and I say you cannot use any built-in Boolean operators anymore, and this is the only operator you can use. Yep.
X NAND X.
X NAND X. Okay, so this is the same thing as X NAND X. So the up arrow symbol, okay, in my notes as well, is representing NAND. Okay. Are we sure this is going to work? Well, let's find out. Because X NAND X is the same thing as the negation of X and X, right? That's the definition of NAND, negation of AND. What is X and X? X. How do you know? Prove it.
Truth table, yeah, truth table.
Because of the truth table. Okay, so let's look at the truth table of AND. So we got X, Y, we got X and Y. 0, 0, we've got a 0, 0, 1, we got a 0, 1, 0, we got a 0, 1, 1, we get a 1. So which part of this truth table is telling you that X and X is X? There are two rows that you need to focus on. The first and the last, right? Okay, very good. So when you look at the first one, 0 and 0 is 0. You look at the last one, 1 and 1 is 1. That explains why X and X is X. Okay? So whenever I tell you or whenever I claim something, you always want to double check and make sure that it makes sense. Okay? And not just superficially or not just intuitively, but logically it can be shown to be true. I know I'm not teaching cisp310, which I also teach on Mondays and Wednesdays, but it should be the same attitude regardless of which class you're taking. Unless the professor doesn't like the attitude. Okay, so are we cool here? The negation of X is X NAND X. Okay, what about AND? In other words, this is what I want, but I only have NAND. What am I going to do? Yeah, go ahead.
Do like not X and Y as like the two operators nested inside of a NAND?
Oh, by the way, I made a mistake here. I should have said, I only want X and Y. There we go.
Yeah, the same. So it'd be like not X and Y and not X and Y. So it'd be like nested NANDs inside of a NAND.
Okay. Okay, so let's see if we can do this step by step. Okay? So would anyone argue that this is really the same thing as X and Y, but with two negations on the outside? Any objections? No? Okay. What if I put parentheses around here? Would that change anything? Doesn't change a single thing, right? But now we do have a negation of a conjunction, don't we? So now we can say, oh, that's a NAND. Okay, cool. Now we can say this is X NAND Y. But we do have a negation on the outside. But we know how to deal with negations, don't we? We know how to deal with negations because of the previous slide. A simple negation means, just NAND that thing with itself. Is that okay? Except in this case, we don't have just a simple X. We have X NAND Y, the whole thing, to be NANDed with itself. So using the previous slide, or using the trick from the previous slide, this becomes X NAND Y, NAND itself. And therefore, we are now boiling down a simple conjunction into just NAND. Is that okay? Is it connecting? Especially the last step, because the last step is the tricky one. The first one, not so tricky, but this one requires you to use the result from the previous slide, that I just talked about. So are we good here? Any questions?
Can you just walk through the last step one more time, please?
Okay. Okay, so when we're on this line, okay, when we're on this particular line, we just want to do the negation of something. Let's call X NAND Y Z, okay? We just give it a name instead of the whole thing. We just call it Z. We just want the negation of Z. The previous slide showed us how to do a negation of something, right? So the negation of something is something NAND that same something. So in this case, it becomes Z NAND Z, except Z is not a simple thing. Z itself is an expression of X NAND Y. So now we have X NAND Y, the whole thing, NAND itself, which is X NAND Y. So is that okay? Cool. All right. So the last one is OR. Okay. How do we express regular logical OR, but only using NAND? Okay. So now we have. Oops. Keep forgetting to switch back to the pen tool. So now we have X or Y. How do we express this as NAND? Well, the first thing we need to do is to say we got to get to at least AND first. Okay? So how do you turn the OR into an AND? The only way you can do it is called De Morgan's law. Okay? But De Morgan's law also requires negation, which we don't have at this point. Well, if you don't have negation, you can always introduce negation. Except when you introduce negation, it always comes in a pair. Is that making any sense? Because double negation is just doing nothing. Are we doing okay?
It's just confirming the truthiness. Well, that's a JavaScript term, but it's just confirming whether it's true or false.
Double negation?
Yeah.
Okay.
Ignoring it.
Well, okay. Double negation means positive,
Right. If
but
it's
double
true.
positive also means negative.
Right.
Yeah, right.
Anyways, moving on. I'm being dumb and talking out loud when I shouldn't.
No, I'm just tagging on that too. Yeah. Sorry, go ahead.
So in the notes here, you're doing C syntax.
Yep.
In the lecture notes you uploaded.
I use mathematical notation.
Mathematical notation, like
Yep.
we did in 440.
Yep.
It feels like I was going through it earlier, and I think you skipped a step. So like.
Oh, okay. So here it is. This is not. This is AND. This is OR. There we go. I'm going to add it back to the notes. Okay. All right. So are we okay with this? You know, I'm just introducing a pair of negations here because double negation cancels out. Okay. So, but I'm just going to do one more step and go like, well, you know, I'm going to do that first and then do that. Is that okay? Okay. So De Morgan's law is really useful because De Morgan's law basically allows you to quote-unquote distribute negation inside a conjunction or a disjunction. But after the distribution, you have to flip a conjunction into a disjunction or a disjunction into a conjunction. Disjunction means or, conjunction means and. Okay. So in this case, I'm distributing this negation. I'm distributing this negation to X and Y. But then I have to change the OR into an AND. So now we end up with not X and not Y. This is called De Morgan's law. And De Morgan's law is really, really useful because it is the one transformation that can go from AND to OR and vice versa. Okay? All right, so now we have an AND. Oh, guess what? We also have a negation to that AND, don't we? Cool. So now we can say we combine. Okay, so let me point out which two we are combining. We are combining this negation with this AND into a NAND. Okay? So we got not X, NAND, not Y. And somebody's going to complain and say, well, this is not all expressed in NAND because we got that negation. But we know how to deal with negation already. Because the negation of X is X NAND X. The negation of Y is Y NAND Y. So now we only have one more step to derive the final result, which is this is X NAND X. That is Y NAND Y. And then the two things are also NANDed together. Is that okay? This is also in the notes, so there's really no need to copy everything, but you might want to write down your own thoughts on this matter. Yep.
If you could quickly explain the transition from the second step to the third step there.
Second to third. So are you referring from this one to this one?
Yeah.
Because a NAND is a negation of an AND. Yep. Is that okay? So this means the operators that you know in C and C++, which is not, and, or, they can all be replaced by a single operator, NAND. Which is really cool. The rest, giving you 3 different ways to express, negation, conjunction, and disjunction is a convenience, but it is not required. Yep.
So do you want us to know how to derive it? Or?
No, I'm not going to ask you guys to derive the expression, but I do want to derive it in the class so that you guys are convinced that this is actually working, this is valid. Yep.
So why are we deriving the expression in terms of NAND from the original disjunction rather than going from in the opposite direction? Why this way rather than the other way?
You mean starting with this and then going back and saying this is eventually X or Y?
Yeah, why do we choose this direction?
Because it is bidirectional. It doesn't really matter which way I derive it, but each step can go in both ways. If I have this step here, I can go back to this one. If I have this step, I can go back to this one. So it's just a matter of choice. But I choose it this way because I want to start with something that you're familiar with and then end up with something that we have just recently talked about.
And the first step to the second step is just De Morgan's law.
Yeah, that's called De Morgan's law. So this one to this one here, this is De Morgan's law. Yep.
Could you explain what, I understand, but I think some people might be helped if you would explain what De Morgan's law is.
Okay, so that's reasonable. So let's go ahead and explain what is De Morgan's law. So De Morgan's law states something like this. It says, if you have a negation, switch back to tool. If you have a negation of x and y, it really is the same thing as the negation of x or the negation of y. And then the opposite is true too, which means if you have a negation of x or y, it really is the same thing as the negation of x and the negation of y. That is De Morgan's law, or the 2 components of De Morgan's law. So of course, you're supposed to ask,
Why?
prove it, right? Well, there's no such thing as y in this particular case, but I can show you the equivalence,
Yeah.
right? So how would you approach this and go why are these, how are these things, how can I convince myself that these 2 expressions, this one versus this one, are really the same? Or this one versus this one are really the same? What trick or what technique are you going to use?
Truth table.
A truth table, very good. So what you would do, I'm not going to do the details here, but what you would do is you would introduce x, y as independent variables. So x can be false, y can be false, x can be false, y can be true, x is true, y is false, x and y are both true. These are the 4 possible ways to configure x and y because they're Boolean variables. And then what you do is you work out, what is the negation of x, what is the negation of y, what is the conjunction of those 2. You fill in this column. Then you go to this one and go what is x or y? And what is the negation of that? Fill in that column. And then what you will find out is those 2 columns look exactly the same. So that's why you can use a truth table to prove that 2 Boolean expressions are equivalent. You cannot use this technique on numerical stuff because there's an infinite number of integers. So you cannot use the same technique to show that x plus y equals to y plus x. There's no way you can do it. But with Boolean expressions, you can do it because there are only 2 values per variable. Is that okay?
Yep.
All right, cool. But thank you for suggesting the discussion of this part here. It will come in handy not only in this class, but also in cisp 440. So if you have not taken 440 yet, this is going to be handy in that class as well. So are we good so far? So far we started out with transistors. or vacuum tubes or relays, and now we have connected those physical devices to logical operators that you already know in C and C++. Not just some obscure gate called a NAND gate, but now we have regular Boolean operators as well. Okay, so we're going to take a short break, not in the lecture, but from the discussion of logic gates. Okay, so we are switching gear to talk about numbers or values, how values are represented. And that part is, I'm just looking up the notes here. So we are moving on to the next document, which is called values, numbers, and bases. So let me open it on tab. And here we go. So this slide is about base conversion. Not only base conversion, but it's actually telling you what a base is and how we actually represent values using a usual way. So instead of reading my notes, which is really boring and I don't like to do it, but you should do it. Well, you can use my notes as a reference. In other words, when you want to read the detail, when you want to actually figure out the rationale and stuff like that, you read that, okay? But I'm just going to go through the overall reasoning of that stuff. Okay, so what we'll do is we're going to look at a number. We'll pick 79 and 0.87, okay? In base 10. So if I don't specify a base, it is implicitly a base 10 number, the usual way that we represent values, okay? Instead of using this as a base conversion problem, let's just say that you're supposed to make this change at the store as an employee to a customer. So can you use the least number of bills and coins to come up with this amount? That's the first question. Can you work at McDonald's? Some of you are not quite sure. Okay, so I'm going to assume the rest of the class is going to yeah, we know how to do this. So how does it work? Okay, so you go like, okay, we need a $50, okay, and then once we are done with the 50, we got $29 left. We have one $20 bill. Then we got $9, right? So with the $9, we got 1, 5, and 4 ones. So that takes care of all the whole numbers. Now we deal with the 87 cents, okay? So we have 3 quarters. To take care of 75 cents, we have 12 cents left. So we got a dime. We don't need any nickels, but we have 2 pennies. Oops, forgot 1 0 here. There we go. Is that making any sense? Okay. If you know how to do this, how come you don't know how to do base conversion? Yep.
Why not use the $2?
Huh?
Why not use the $2?
Because most people do not have $2 bills. So I'm only using the more common coins and bills, because we do have half dollars too. Okay, but if you can do this, you know more than you know already. More than you think you know. Okay, you know more than what you think you know. Because if you can do this, this is harder than base conversion. Why do you think this is harder than base conversion? Yep.
Because it has inconsistent differences between the sizes.
Right, exactly. The multiplier between the amounts is not regular. Okay, so let's take a look. We have a penny. The next one up is a nickel. Then the next one up is a dime. The next one up is a quarter. The next one up is a dollar. Then we have $5. Oops. Then we have $5 bills, $10 bills, $20 bills, $50 bills, and $100 bills. And then you look at the multiplier between each one, okay? We got a 5 here, we got a 2, we got a 2.5, and then a 4, and then a 5 again, and then a 2, and then another 2, and then another 2.5, and then another 2. I don't see any regularity here. Okay, maybe it's just me, but I'm not seeing any regularity. And yet you can deal with it, right? What if I am to propose a new currency system? Look at this. Huh? Sorry? Crypto? Well, how the currency represents value is not the key. Okay? The key here is what is in your pocket. Okay? So we'll have a dollar. Okay, we start with $1. The next one is $2 bill, $4 bills, $8 bills, $16 bills, 32, 64, and so on. Do you see any regularity? They're always doubling, right? And on the other side, I'm always going to divide it by half. Okay, so I'll give you a $half coin, a quarter, eighth, and 16th. This is the new currency system. All right. Now the amount that we were just working with is not going to work well with this. Okay, so I've got to give you a new amount to work with. So let's try $91 and $875. Okay. How do you make change for this amount when you can only have those bills and coins and use the least amount? So don't tell me I'm only going to use $16, just a whole lot of those. Okay. Okay. How do you decide that you should start with 64? Because 64 is the largest power of 2 that is less than or equal to the amount that you're dealing with. Okay? All right, so you have a 64. After the 64, then what? Do you need a 16? Yep, you need a 16. So after the 16, you got 11 left. So with the 11 left, you will need an 8. After the 8, oops, I just clicked a button. Sorry. There we go. The power key is being bumped because it's bumping up against the, there's a little edge on the podium, so it's bumping up against that, so it's turning itself off. Okay, so we have an 8, but after the 8, we only got 3 left, so we don't have any 4s. So with a 3, we got a 2 and a 1. Okay, that takes care of all the whole number. So now we have 0.875 left. That will involve a half, which is 0.5. And then after that, we got 375 left, 0.375 left, which means there's a quarter, right? And an eighth. There are no 16th. Cool? Okay, so now how do we look at this as a binary number? Okay, so we got one of these, 0 of the 32, right? One of the 16, one of the 8, 0 of the 4, 1 of the 2, 1 of the 1. And then on the other side, we got 1/2, 1/4, 1/8, and 0 of the 16th. That's a binary number. You just have to tilt your head a little bit. Which way do you tilt? When most significant digits are on the left-hand side. Do you tilt clockwise or counterclockwise? Your clockwise and your counterclockwise. Your clockwise, exactly. Okay, so I think administration will now start to notice how come students of your class tend to have neck issues, neck injury, right? Yeah, so if you tilt your head this way, then it becomes a binary number. The binary number is 101111.1110. Is that okay? Yes? All right. So I see some doubts in amongst you guys. So we'll start with the same number as last time. So we'll have what was it, 91.875. But this time I'm gonna look at this as just a straight base 10 number, but we'll break it up. Okay, we'll take it apart. Would anyone argue about this equality? Nope. Okay. What about this? 9 times 10 to the power of 1 plus 1 times 10 to the power of 0 plus 8 times 10 to the power of negative 1 plus 7 times 10 to the power of negative 2 plus 5 times 10 to the power of negative 3. Is that okay? What is that showing you? Is there any type of pattern here? There's a pattern here because each digit that we use is specifying a particular the quantity of a particular power of 10 in this case. Just like in the previous slide, each digit is telling you the presence or the absence of a power of 2. Is that okay? All right. So let's abstract this one step. Okay. When we abstract this one step, we're basically saying let's lose some unimportant detail. Okay. In other words, I'm just going to call this one D0. Okay, which is the unit digit. I'm going to call this one D1. This is going to be D subscript minus 1, D subscript minus 2, D subscript minus 3, and so on. Okay? Do you see how I number the digits? What do you see that is corresponding? Oops. Yeah. This time it's the PC. Okay, there we go. So what do you see that is mapping from the subscript of the D versus the power of 10? They match, right? D0 specifies how many 10 to the power of zeros do we have. D1 specifies how many 10 to the power of 1s do we have. D subscript negative 1 tells us how many 10 to the power of negative 1 do we have. Is that okay? In other words, the value being represented by the number is now saying, oh, it is D1 times 10 to the power of 1 plus D0 times 10 to the power of 0 plus D negative 1 to the times 10 to the power of negative 1, blah, blah, blah. Right? So this is abstracted a little bit. But you can see every time I use the dot, 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 it means it's tedious. I don't like things that are tedious. So is there an easier way to express something like that? How about sigma, the summation symbol? Okay? So I'm not going to specify where we start and where we end. I'm only going to specify that I is the index of the summation. So what are we summing? We are summing D subscript I times 10 to the power of I. And where we start depends on what is the least significant digit you want to deal with. Okay, you can start with negative 4. What is the most significant digit that you want to deal with? Okay, I'm not that rich, so I'm going to stop here. Anywhere beyond that is useless to me, because all the digits beyond that point are zeros. Is that making any sense so far?
Yes.
Okay. How many people have looked at numbers this way? Next time you go to Walmart, you look at the price of something, you go like, ooh, I see patterns. But okay, but that's one more thing we can do about this. Okay, what if I say, oh, forget about base 10. That's an arbitrary base only because we got 10 fingers. Okay, change that to B for base. So now you can now understand how we can represent a value in different bases. Base 10 is just what we are used to, but it's not the only base that we can use. We can use base 2. Okay, now base 2 is particularly important. Why? Because it ties into something that we have been talking about already. Binary. But why do we care about binary? Zeros and ones. Is the transistor on or off, right? Okay, so we care particularly about binary, but there's no one saying that you cannot use some really oddball base like base 7. Okay, octopi may choose to use base 7. Then you go like, but octa means 8. I know that, but you need one tentacle to hold a beer. Right? So you only have 7 left to do the counting. So therefore, they want to use base 7. See, humans know nothing about fun. We use all the fingers available to do counting already. So there's nothing left to do something fun. But that's only because octopi do not live very long. Gotta enjoy life if you have a short life.
So are you saying we should go to base 12 so we can count on one hand?
Or you can use your toes.
Yeah, base
We can still use one hand, if we're using base 5. So let's explore base 7. Let's see if we can deal with base 7, okay? So I'm gonna open the new slide here. We'll pick a value in base 10 so that we can at least specify that amount. 107, okay? This is in base 10, so this time I'm using a subscript of 10 to indicate this is a base 10 number. I want to figure out how to represent this in base 7, okay? Some really oddball base that you will never see again, okay? So the first thing you need to know is, okay, what is the largest power of 7 that is less than or equal to 107? 49, yeah, 49 is it, right? Okay, so how many 49s do we have in 107? Two of those, okay, so we got 2 times 49 plus, what is left? Okay, I cannot do my math. 2 times 49 is 98.
So there's 9.
There's 8 left? There's 9 left? Okay, so if there's 9 left, you got 1 7 and 2 1s, right?
Where did 49 come from?
Because 7 times 7 is 49. 49 is a power of 7.
7 times 8, we can't use 56 now?
No, because you have to use powers of 7 only.
Oh, powers of 7.
Right. Just like, when you're dealing with base 10, each digit is indicating the quantity of a power of 10. So in this case, each digit is telling you the number of powers of 7s. Okay? So that means that this number can be expressed as 2, 1, 2 in base 7. Is that okay? So using this trick, you can always claim to be 11 years old. We just changed the base. Every year, we up the base by 1. Now, there's a minimum age that you cannot bypass, okay? Because base 2 is the smallest base. So that means, from year 3 and on, we're always 11 years old. You don't have to buy new birthday cards anymore. Cool. So are we doing okay so far with base? But do you see how a value can be represented in any number of bases? Okay, so that's really important because what we see as a number, like 107, is really just a representation of the quantity that is behind the scene. Is that okay? All right. So if you go to the notes, okay, we talk about all of this stuff here, which is already covered in the notes. But the base conversion part is kind of tricky. So if you want to convert a particular value v into whatever base you choose, there's a really easy equation to do it. So you're supposed to read all of this stuff here, but I'm skipping to the actual result here. If you only care about a particular digit, let's say that digit is d subscript I, and remember, I doesn't start from just anywhere. D subscript 0 corresponds to the number of b to the power of zeros. Okay, d of I, or di, is representing the quantities of b to the power of I. So you got to remember that part. Are we cool with that? Okay? So this is an equation to basically let you convert to any base, and you can pinpoint each digit of that base just like that. This symbol is representing the floor function. The floor function is kind of a rounding thing, but it's not. Because when you use the floor function, it returns the integer that is the largest integer that is less than or equal to whatever you are flooring. Is that okay? The cricket is being very disruptive, but I cannot drop that. The cricket is not on my roster. I cannot drop the cricket. I suppose I can drop it in a different way. I got a assault gun. The campus police may have a problem with that. Wait, assault gun has no fire, right? So it's not a firearm. But okay, let's check this out, okay? Because we just did some really oddball conversion from base 10, quantity that was originally base 10 into base 7, right? So we can use this to check whether that works or not. So let's go ahead and check this out, okay? So I'm gonna put my tablet thing next to that equation so that this way we can look at the equation and at the same time look at the derivation. So I used the wrong pen. I almost used the wrong pen on my tablet. Look at the similarity. It's not a coincidence. I specifically buy this stylus because it looks like a real pencil. So the fault is mine. Okay. So we are basically saying the base is 7, so B equals to 7, right? And we'll start with D. We can pick something that's not even in here. Okay, we'll say D3. So D3 is the floor of 107 divided by 7 to the power of 3, and then the whole thing mod 7. Okay? What is that going to be?
107 divided by
343.
343.
43, okay, thank you. And then the whole thing mod 7. What is that going to be? Yep.
I don't understand what D is.
D is digit.
Oh.
So this is the digit representing the quantities of 7 to the power of 3. In other words, we're trying to express the number as D0, D1, D2, D3. So we are focusing on this guy at this point.
Right.
Okay? And do you guys agree this is going to be 0? Because 107 is less than 343, so the amount is already less than 0. But when you take the floor of that value, you just get 0 back. Because 0 is the largest integer that is less than or equal to about a third in this case. Yep.
So this floor, does it round it or does it truncate it? Like,
It's neither. It is returning, as I said, the largest integer that is less than or equal to whatever is inside the floor. Yep. So it's actually neither. Yep. So this is actually 0. Okay, fine. What about D2? So D2 in this case is 107 divided by 49, but we take the floor of that division and then we mod it with 7. So this is 2 point something, right? 2 point blah blah blah. Take the floor of that, mod 7, then it becomes 2 mod 7, which is 2. Is that okay? So we want to check the other two, okay? We want to check D1, D0, we want to check D0. So I'm running out of space here, let's put it just here. D0 is 107 divided by 1, the whole thing mod 7. Because 7 to the power of 0 is 1. Okay? Alright, cool. So this whole thing is now just 107 mod 7. And what is that?
2.
So it's the remainder of 107 divided by 7. So if I just do it, using my mental math. So, okay, 107 divided by 7 is 1, 7, and then we have 37 remaining. And then we have 5 of that. Okay, so we have 15 with a remainder of 2. So we got that 2 back. We got this 2 back, which is the number of ones in that number that is in base 7. Is that okay? And you can even apply this to the binary number that we were working on earlier and look at the fractional part. Because it also works. When I is negative, it still works. And that's the cool part of this particular definition is you can pinpoint and get to a particular digit of any base. Is that okay? So that makes base conversion really easy because you just kind of plug in the numbers and go through this calculation and do it, x many times for x many digits, and you're done. Yep.
Is the answer 2 for the 107 mod 7?
Say that one more time.
Is the answer 107 mod 7 2?
Yes, that is in fact 2. Yep. Go ahead.
So 107 has to be in base 10?
107 is in base 10 because I need some default base when I try to specify a quantity. Because the only other way that I do not use a base to represent a quantity is to draw 107 apples. Which may not be a good use of our time.
But can 107 be in a different base? Or?
Yes, it can be, but not in this case, because if I use any base other than base 10, I have to specify what base it is. And therefore the problem, therefore the observation that we are always 11 years old. Okay, what we see as 11, which is actually the quantity of 10 plus 1, is represented as 1, 1, right? But if you choose your base, then you can always say it is 1 times 1 plus 1 times whatever base to the power of 1. So you can use that trick to always claim that you are 1 years old. You just change the base. When you're supposed to be 4 years old, you change the base to 3. 1 times 3 plus 1 is 4. When you're 87 years old, you change your base to 86. So it becomes 1 plus 1 times 86. So it's a trick. So are there any other questions at this point about base conversion?
Have you thought about bringing this idea forward to 4 over 21?
Say that one more time.
Have you thought about bringing this idea to 4 over 21?
Oh, that is funny. Yep.
Can you just explain again real quick the floor? Because it specifically deals with whatever base we are trying to get to.
Nope,
right?
floor has nothing to do with base. Okay, so the floor of x is defined to be the largest integer that is less than or equal to x.
Okay.
So that's the definition of the floor. So I'll give you some examples. The floor of 3 is easy, right? Because the largest integer that is less than or equal to 3 itself is 3. Okay, that's easy. 3.5 is also 3. 2.9 is 2. Negative 1.1.
Negative 2.
Negative 2. Okay, not negative 1. Because negative 2 is the largest integer that is less than negative 1.1. Okay, so it's not, that's why I said it's not rounding, nor it is truncation. Depends on the sign of the value. All right, so we are moving along. So dealing with binary numbers is it's easy because once we have this equation, it applies to binary number 2. All you have to do is to change b to 2. Then you know how to represent values in base 2. That's just what it is. If I give you a binary number, how do you know what value it is representing? You go back to the sigma notation. If I give you a binary number, which means I give you a bunch of di's, and b is 2, you just use this summation to figure out the value that is represented by the binary number. So now we have it going in both ways. If I give you a value, you know how to convert it into base 2. If I give you a binary number, you know what value it is representing. Are we doing okay so far with this? But I will say one thing, binary numbers are really easy to deal with because there's no division. Conversion to base 2 there's no division needed. There's only comparison and subtraction. Why? Because for any power of base 2, you can either have 0, or none of those, or just 1. So that's why you're only comparing. If the number you're converting is greater than or equal to a power of 2, you have one of those powers of 2. Otherwise, you have 0. So that's why the conversion into base 2 is actually easier than any other base. So are we doing okay so far in this class? Okay. So the next slide, because we are running out of time, we got 2 minutes left. Okay, so let me go back to the main catalog here. So the next slide that we're going to talk about, if you have time over the weekend, please read ahead of me. This one talks about binary number addition. Okay, and it will prove that we chose the wrong base. We chose the wrong default base. You will go back to your elementary school teacher and go like, why? Okay. Because if you think about it, okay, we still got 1 minute, at least 1 minute left. This is all the time that I need. What is the size of the multiplication table? Or worse yet, what is the size of the subtraction table? In other words, how do you know 3 minus 7 is 6 with a borrow? So technically speaking, that table is 10 by 10. Okay, because we got 10 digits in base 10, so I can always ask, okay, what is this digit minus that digit, right? And because subtraction is not commutative, you cannot just say, oh, the other half looks exactly the same. No, it is not the same. So that's why in the subtraction table, it has 100 items. Now, out of the 100 items, you can always claim that whatever minus 0 is just whatever left, okay? So you can say that row doesn't need to be memorized. But you still have 90 items in that table, okay? And it takes a long time to do it too. In binary subtraction, the entire table has 4 entries. All those weeks, all those months, all those agony in elementary school to learn subtraction and multiplication and stuff like that could have been done in a day. Okay? So if I were a politician, I would use binary numbers as my platform. Forget about the rest of the issues. I'm just changing the base of how we represent values. And then you guys will go like, oh, yeah. All right, I'll see you guys on Tuesday, and please read about the addition in binary numbers because that's actually important.